let's start. How many of you took a look at the exercise? Is it okay? Do you have any problems with the exercise?
I wrote it off. I just didn't have time to reply to you. Like, question 3 will be kind of a paradox.
Okay. So
I don't know what you want us to write about.
Think about it. We want you to think about it. Do your best. And if you just understand the paradox and explain it, then you're okay. But try to solve the paradox. Okay? Do your best. It's okay. We know it's a tricky question. Okay? We just want you to really, really think about it. Okay? And show us that you thought about it. Any other questions about the exercise? If there are any questions that you had a particular problem with, let me know and I'll solve them in next week. Okay? So don't worry about it. Okay. So what are we going to do today? We're going to finish the probability recap that we started last week. That will be the first hour. In the second hour, we'll start reviewing the material that you saw in class. Okay. Let's start. So last week we talked about events and probabilities and what is a random variable. We refreshed your memory about all these things. And today we'll start to look on special distribution, special random variables. Okay? So the most basic distribution is the Bernoulli distribution. Okay? Which is a distribution over a binary random variable. Okay? So suppose x belongs to a binary set. You can take two values, 0 and 1. Okay? You can rename them as head or tails, whatever you want. Okay? And we denote this that as x is distributed according to the Bernoulli distribution with one parameter p. Okay? And the distribution is given like this. P of x is p, small p, if x equals 1, and 1 minus p if x equals 0. Okay? So there's only one parameter in this distribution. Okay? So what is the expected value of x? Anyone? P, right? What is the variance of x? Okay, so let's do this one together. So the variance is the expectation of x minus the expected value of x, which is p, right? To the square. Okay? Which is p times, p is the probability that x is 1, times this term when x is 1, which is 1 minus p to the square, plus 1 minus p, which is the probability that x is 0, okay, times 0 minus p to the square. And if you open up the parentheses, you just get that the variance is 1 minus p. Okay? I'm sure you've all seen this before, but it's nice to refresh your memory about that. Okay, now suppose that we have n Bernoulli random variables. So we have x1 to xn, and suppose that they're all independent, identically distributed according to the Bernoulli distribution. Okay, so we denote this as IID, independent, identically distributed, okay, according to the Bernoulli distribution with parameter p. Okay, so this notation is clear to everyone? Did you already see the term IID? Okay, very good. Now we want to let's look at the random variable x. Yes?
I think the variance should be multiplied by p.
Yeah.
Because if p equals
Yes. Of course. Now let's take a look at the random variable x, which is the sum of Bernoulli variables. Okay? Sum of xi. Okay? How is this random variable distributed? It's the binomial, right? So this is the binomial distribution. which I'm sure you've all seen already. And what is how is this random variable distributed? So first of all, what is the possible values that this random variable can get?
Like 0.
So x belongs, x belongs to the set 0, 1, and so on till n, right? Because we just count here the number of ones that we got in a sample of Bernoulli variables, right? So this is the possible values of x. So it's a discrete random variable, of course. Okay, and what is the probability that x, the random variable, equals some k? Okay, where k belongs to this set. So what is this probability? So suppose that we are given a specific sequence. Okay, so we have a specific sequence of results. Suppose we toss the coin n times, and you get a result of the first toss, second toss, and so on. And suppose 1 indicates that we got heads, and 0 indicates that we got tails. Okay, we want to count the number of heads that we got. So for this specific sequence, what is the probability that we got k heads, k ones, in one specific sequence?
And choose k.
No, in one specific sequence. Okay, so
To the power of
p.
p. To the power of k.
Very good. So we got k ones, okay, and they're all IID. So the probability of getting k ones is p to the k, and then we got n minus k zeros. So the probability of getting n minus k zeros is 1 minus p times n minus k. And as you said, remind me your name? Tovia said, we have many options for getting this. It's not just a single sequence, right? And the number of all the options of choosing k1s out of n instances is n choose k. Okay, and just to remind you that n choose k is n factorial divided by k factorial times n minus k factorial. Okay, because we don't care about the order of the sequence. Okay, so there are many sequences that will give us k1s and n minus k zeros, and they're all equivalent in this case. For the sum, they're all equivalent. Okay? So this is called the binomial distribution. It's a good exercise to make sure that it's indeed normalized. So if you sum here over all possible values of k, then you get 1. Okay, that's a good exercise for home. But let's evaluate together the mean and variance of this random variable. So what is the expected value of x? Okay, so let's write it more explicitly. I'm going to substitute here the sum. Okay, so this is just the expected value of the sum of xi. But we know that the expectation is linear, which means that we can take the sum outside of the expectation. Okay, so this is just the sum of I from 1 to n of the expected value of xi. And what is I'm sorry, this distribution has two parameters, n and p. I'm sorry. Okay, and what is the expected value of each xi? I'm sorry. This is correct. What I meant to write is, this is Bernoulli. This is correct. What I meant to write is that the notation here is that x is distributed according to the binomial distribution with two parameters n and p. This was correct. I'm sorry. So yeah, who said p? All of you. Okay. So the expected value of this is indeed p. Okay, and so we have n times p, so the expectation is n p. Okay, and what is the variance of x? So as before, it's the variance of the sum of all xi. And what do we know about the variance of sum of independent random variables? We saw this last week. So if we have a sum of independent variables, what do we know about their variance? Right. Okay? So the variance of the sum of independent variables is the sum of the variances. So again, we can take the sum outside of the variance. Okay? So this is just the sum of I goes from 1 to n of the variance of xi. And once again, since they're all distributed according to the Bernoulli distribution with parameter p, what is this? It's written on the board. Very good. P times 1 minus p. And then we get that the variance of the binomial distribution is n times p 1 minus p. Okay, any questions about this?
Do you need the fact that there are IID4 and the average of the sum to be sum of averages or not?
You're talking about expectations?
Yeah.
No. Okay. Okay. So the next distribution we'll talk about. Move this here. Is the Poisson distribution. Okay, this distribution has one parameter, lambda. So we denote x. Poisson variable x is distributed according to the Poisson distribution with parameter lambda. Okay, this distribution is used to model cases where we want to count the number of events that occurred at a given time unit. Okay, so for instance, you can think about if you want to find the distribution of the number of customers that arrive at a store within an hour. Or if you, from LSAT, then you might want to think about the number of spikes that a neuron fires within, I don't know, a certain time interval second or something like that. Okay? And lambda is the rate parameter. Okay? So just notice that this distribution, okay, so far we saw two discrete distributions, the Bernoulli and the binomial, which were over a finite domain. Okay, this is also a discrete distribution, but here x could be 0, 1, and so on. It could be any natural number and 0. Okay, so this is a discrete distribution over an infinite domain. Okay, it's countable, but infinite. Okay, so this is the probability that x equals k. Okay, for k in this range. Anyone remembers what it is? You don't have to remember that, but
Sure.
okay. So we have lambda k e to the minus lambda divided by k factorial. Okay, and again, it is a good exercise to make sure that that this distribution is normalized. What is the expected value of x? Lambda. Very good. I will not prove this. If you're not sure how to show it, take a look at my notes. I'll upload them afterwards, and you can see the proof there. I assume that you all seen this already and more or less know how to do that. What is the variance of x?
Lambda minus lambda squared.
That's a wild guess. It's lambda as well. So this is one of the special properties of the Poisson distribution, that the mean and variance are equal. Okay, so this is a nice property of the Poisson distribution. Okay, let's do a simple example or a simple exercise. Okay, suppose that we want to find the distribution of the time intervals between two events, two Poisson events. Okay, so for instance, if we want to find the distribution between two consecutive spikes of a neuron, or any events that are distributed according to the Poisson distribution. Okay, so suppose this is our time. Suppose at time 0 we had the first event, and suppose that at time t, capital T, we had a second event, and in between there were no events. Okay? And we want to find the distribution of t. Okay? The question is clear? Yes? Okay, very good. Okay, so to do that, first let's note that let's define the random variable xt, okay, which is the number of events that occurred at t time units. Okay, so if we know that in a single time unit, the number of events is distributed according to the Poisson distribution with parameter lambda, with rate lambda, then xt is distributed according to the Poisson distribution with parameter lambda t, okay, because we're stretching it over t times t. Okay, we're accumulating events over t times t. Okay, so now if t is here, what do we know? Okay, if capital T is bigger than lowercase t, then what do we know about the value of xt? 0, right? So what is the probability that capital T is bigger than small t? It's just the probability that xt equals 0, right? And this is just the Poisson distribution. We just substitute in this distribution 0. Okay, so this is lambda t to the power of 0, e to the minus lambda t divided by 0 factorial, which is e to the minus lambda t. Okay, and now we can find the probability that t is at most t. Right? This probability is just 1 minus e to the lambda t minus lambda t. Okay? xt is the number of events that occurred at t time units. Okay? When we know that in a single time unit, the number of events is distributed according to the Poisson distribution with parameter lambda. So over t time steps, time units, the rate is lambda t. Okay? Just accumulate events. Okay, and what is this guy here? We defined this function last week. How do we call it? Remember, t here is a continuous random variable. It's positive, but continuous. So how do we call this function? Exactly. So this function here, this guy, is the CDF of t, right? And from here, how can we find the density of t? You started to say that? You differentiate with respect to t, right? So f of t, okay, here is t of f t of t. The density function of the random variable t, a value t, is lambda e to the minus lambda t. Okay, just differentiate this with respect to t. Okay, and of course, this is when t is greater than 0 and 0 else, because t is positive. Okay, this is clear? Anyone knows what's the name of this distribution? This is the exponential distribution, very good. Do you see it right here? Do you see it here? Okay, so x is distributed according to the exponential distribution with parameter lambda, the same parameter. If it has the density function, exactly what we wrote there, lambda e to the minus lambda x, if x is positive, but it could be, now it's a continuous random variable. Okay, so it can be any real positive number, and 0 else. Okay, what is the expected value of x? Anyone remembers? Okay, so you can verify at home that the expected value is 1 over lambda, and the variance of x is 1 over lambda squared. Okay, so this was the exponential distribution, and it's the first continuous distribution that we discussed so far. Okay, the next distribution is actually the exponential distribution is a special case of the next distribution, which is the gamma distribution, and it's also a very useful distribution that we will see in the course. I assume not all of you have seen this distribution before. Okay, so this distribution has two parameters. It has parameter alpha and beta. Okay, and both of them should be positive. Okay, and it is given according to the following density function. Okay, so the PDF of x is beta. I don't expect you to remember that, okay? But it's good to know anyway. So it's beta to the power of alpha x alpha minus 1 e to the minus beta x if x is positive and at 0 else.
You said e to the negative beta x, or just e to the negative b?
Oh, I'm sorry, what? I forgot to do something.
To the minus beta x, or...
And the exponent is the m.
And the gamma function here. Okay, and the gamma function is given, gamma alpha is the integral from 0 to infinity of x alpha minus 1 e minus x dx. Okay, so it is easy to verify that the gamma function of 1 is simply 1, right? Okay, verify that. And you can verify that for any alpha that is greater than 1, we have that gamma alpha equals alpha minus 1 gamma of alpha minus 1. Okay? So if this function seems a little bit strange to you, you can think about it as the continuous extension of the factorial function. Okay? And these two properties give you exactly why. Because from here, okay, and it's easy to show these two properties, okay? Just substitute and integrate and just think about it all. Okay? And the integration by, I think integration by parts solves this. But it's not that hard. But if you have these two properties, then you can show that for any natural number, okay, gamma n is the n factorial. Okay? Oh, n minus 1, I'm sorry. It's n minus 1 factorial. So, in this sense, the gamma function is a continuous extension of the factorial function. Okay? And what is, let me write it here. What is gamma of 1 and lambda? It's exactly. It's the exponential distribution with parameter lambda. Okay, any questions? Okay. And now finally we get to the distribution that I'm sure you've all seen many, many times, which is the normal distribution. So far both the exponential distribution and the gamma distribution were continuous, but only over the positive numbers. Yeah?
I just want to understand what it means to have an extension of factorial on continuous numbers.
Mm-hmm.
So what does that mean?
That is...
No, I know what it means for discrete numbers.
Okay, it's a continuous function
Yeah.
that for each natural number, it has the same value of the factorial function. Okay, so it continuously connects these values.
But if I have the gamma function of 2.5, is there an intuitive meaning of what that is?
Besides, that's the intuition, but I can try to think of a better explanation for next week if you want. Okay. The next distribution is the normal distribution, okay, or sometimes it's called the Gaussian distribution, okay, which is, I'm sure you've all seen this many times, probably one of the most popular distributions, okay. So this distribution has two parameters, okay, so we say that x is normally distributed, we denote it with the letter n, with two parameters, mu and sigma square, okay, and the density function of x is 1 over square root of 2 pi sigma square exponent of minus half x minus 2 sigma square x minus mu to the square. Okay? What is the expected value of x? You all know this. Mu, right? And what is the variance of x? Sigma square, right? Okay, so this distribution has the very famous bell shape that I'm sure you've all seen. Okay, so just make sure that you all know. So it's concentrated around the mean, okay, and its width is about sigma, which is the standard deviation. Okay, so a few very important properties of the normal distribution. So if we have, suppose that x is a normal distributed according to the normal distribution with mu and sigma square. Okay, so what can you tell me about y that is ax plus b, where a and b are just constants? First of all, what is the expected value of y? A mu plus b. What is the variance? No. Yeah, without the b. Okay, the constant does not affect the variance. Okay, but if you multiply, then it goes out with a square. Okay, so exactly, and y is also normally distributed, but with the mean and variances that you just said. So with mean a mu plus b, and variance a square sigma square. Okay, so this is one important property. And it's true also for sum of random Gaussian variables. Okay, so if you sum a few random Gaussian variables, this is also true. We'll probably write it in a second. Suppose, let's look at the random variable z that is defined by x minus mu divided by sigma. How is this random variable distributed? It's distributed according to the normal distribution with mean 0 and variance 1. And we call this the standard normal distribution. Okay? And we denote the CDF of z, we denote by phi of z. Okay? So, what is the connection between the CDF of x and phi, the CDF of z? Okay, so the CDF of x, f of x, is just the probability that x, the random variable, is at most the value x. Okay? This x and this x are the same. Okay? Which is the probability that sigma z plus mu is at most x. Right? I'm just substituting. Which is the probability that z is at most x minus mu, the value x, divided by sigma, which is phi of what? X minus mu divided by sigma. Okay? So basically, if we know the CDF of the standard normal distribution, we can evaluate from that a CDF of any other normal distribution. Okay? And the CDF, we don't have a closed form for that. We need to evaluate numerically. Okay? Any questions so far? I assume you all know this, right? Yeah.
What's the main variance of the Gaussian distribution?
Oh, excellent question. I forgot to mention that. So, let's write it here. So the expected value of the gamma distribution is alpha divided by beta, and the expected value and the variance is alpha divided by beta squared. Okay. 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 The next property of the normal distribution, I actually already mentioned it, but let's write it down anyway. Suppose we have x1 to xn, okay, which are independent. This is an important assumption here, okay, such that xi is distributed according to the normal distribution with mu I and sigma I squared. Okay, and now let's look at y, that is the sum of xi. Okay, so y is distributed according to the normal distribution as well with, what is the mean? Yeah, you started to say that? Sum of mu I. And what is the variance? Sum of sigma I squared. Okay? And it's important that they're independent. If they're not independent, then it's no longer true. Not necessarily true. Okay? And another, we haven't talked about multivariate random variables so far, but it's very useful to know the multivariate normal distribution. Okay? So when we talk about a multivariate random variable, so just to remind you, a random variable, a real valued random variable, was a function from the sample space to the real numbers. Okay? A multivariate random variable is a function from the sample space to Rd. Okay? That's all. So now it's just a vector, just as not a scalar. Okay, so let's denote x as a vector x1 to xd. Okay, so it has d coordinates. Okay, and now we can talk about mu, which now would be a vector of means. So mu I is the expected value of xi, and instead of variance, okay, we have a covariance matrix, because we need not to account only for the variances of each coordinate, but also for their interactions. Okay, so we have a covariance matrix which we denote as sigma, where sigma ij is the covariance between xi and xj. Okay, and what do you know about covariance matrices? It's symmetric, right? What else do you know about it? And the diagonal is the variance. Very good. What else?
Invertible.
Okay, that's tricky. It's almost invertible, but it's okay. So covariance matrix is positive semi-definite. Okay, so let's define a positive semi-definite. or PSD. Okay, that's the usual term. So a matrix is positive semi-definite if for all x in, say, Rd, in our case, x transpose sigma, or let's say m, it's more general than sigma, m x is greater than 0, is non-negative. Okay? So for your comment, if it's positive semi-definite, it might have eigenvalues which are 0, and therefore it's not strictly invertible. Okay? However, if it's a positive definite, okay, which means that for all x in Rd which is not 0, x transpose m x is positive, strictly greater than 0, now it's invertible. Okay? And we would usually assume that the covariance is positive definite. Okay? Because try to think what happens if it's not positive definite, if there is an eigenvalue that is 0. Okay? It's somewhat degenerate. Okay? So the interest case in most cases that we will discuss in this course is when the covariance matrix is positive definite. Okay? And in that case, if it is positive definite, then we have a PDF, a density function for x. Okay, so now I'm just reminding you that x is a vector, so that PDF, the density, gets a vector, but it returns a single number, so it's still a scalar function. Okay, so the PDF of x, in this case, is 1 over square root of 2 pi to the power of d times the determinant of sigma. Okay, and the exponent of minus half x minus mu transpose sigma minus 1, the inverse covariance, times x minus u. Okay? So this is the multivariate normal distribution. Any questions on this?
So that's only if it's positive definite?
Yes. Because what will happen, so, okay? Or you don't have this even, if it's not invertible. Okay, but you can assume, okay, unless, in this course you can assume that it's positive definite. Okay, you don't need to deal with the case that it's semi-definite. Alright.
So can you just maybe remind us for a second the relationship between that equation of x transpose m x and the eigenvalues?
Between this?
No, just above there. The
This.
relationship between those equations and the eigenvalues.
Between, why do I say?
Yeah.
Yeah, so it's actually it's a little bit beyond the scope of this course, but you can show a few equivalent conditions or characterizations of positive semi-definite. So one of them is this, and one of them is that all the eigenvalues are non-zero. So for instance, so it's symmetric, right? So you know that it's diagonalized, right? So if you take the eigenvectors here, then you just simply get the eigenvalue, and it's not positive, and non-negative. Okay, so substitute x, this needs to hold for all x. Substitute x by the eigenvectors, and so you get that this is the eigenvalue. Okay?
So it's like PDP equals lambda. Okay.
PDP.
Like when you have a diagonalizable matrix, we have P times the matrix times P transpose equals by the diagonal matrix. Then that's what's going on there.
So the P is the matrix. Let's talk about it in the break because I don't think everyone. But the P is the matrix of eigenvectors. Let's talk about it. Okay. Any other questions about this? Okay, very good. So let's see how are we in time. Great. So we have 3 minutes to discuss limit theorems. So one of the nice properties of the normal distribution is that it gives us that we know that if we have a sample of n IID random variables, okay, we know that their sample mean, their average, how is it distributed? What do we know about that? Okay, I'm sure you've all saw the central limit theorem, right? So it's I'll remind you this in a second, but it's distributed according to the normal distribution, or at least as n goes to infinity, the distribution of the sample mean converges to the distribution of the normal distribution. Okay, so this is one of the reasons that we're so interested in the normal distribution. But okay, so let's start to define this more accurately, and I'll just remind you two limit theorems that tells us something about the sample mean, how it's distributed, and where it converges to. Okay, so this is limit theorems. Okay, so suppose we have x1 to xn, which are IID. Okay, according to any distribution. I don't know. Okay, all I need to assume, or all I want to assume now, is that I have finite mean. So the expected value of xi is mu I. Okay, and I'm sorry, is mu. They are identically distributed. Okay, and that they have also finite variance. So the variance of xi is sigma squared. Okay, this is for all I. So we define the sample mean, or empirical mean. Okay, we already saw this, something very similar to that in the binomial distribution, but then we just took the sum. Now let's take the average, so it's 1 over n, sum I goes from 1 to n, xi. Okay, so what do we know about the expected value of x bar? It's mu, right? Okay. X bar is this. This is the definition. This is how we define x bar. It's the average. It's a new variable. So we have xi to xn IID random variables with mean mu and variance sigma square. And now we define the empirical mean.
Okay, it's not a vector.
No, it's not a vector. Okay, I denote a vector with an arrow.
Okay.
Okay. It's confusing. We wanted to write x bar n to remind you that it's an average over n variables. Okay, it's a standard notation, by the way. This is standard notation, this is standard notation, so you'll see that in many books, so actually it's good to get used to that. Okay, so the expected value of x bar is the expected value of 1 over n, sum I goes from 1 to n, xi. Okay, and again, the expectation is linear, so we can take 1 over n and the sum outside. Okay, and then we get 1 over n sum over I of the expected value of xi, and since they're all IID with mean mu, this is mu, as you all said already, so we have n times mu divided by n, which gives us mu. Okay? Great. What is the variance? We'll do the variance and then we'll take a break. What is the variance? So the variance of 1 over n sum of I xi, notice that this is a constant, right? And this is some random variable. Okay, so if you have a constant multiplying our variable within the variance, what do you know about this constant? Constant, it goes out of the variance squared, right? So this is 1 over n squared, the variance of the sum over I of xi. And what do we know about this? I remind you that they are independent. So we take the sum, we can take the sum out of the variance because they are independent. Okay? So this is 1 over n squared, sum over I of the variance of xi. And now, since they're all have the same distribution, this is sigma squared, and we have n times sigma squared divided by n squared, which is sigma squared divided by n. Okay. So what happens when n goes to infinity? It goes to 0. Right. And we'll continue after the break. I haven't uploaded these notes yet. I'll do that. The previous ones are in the middle. I'll upload these before the next one.
אתה יכול לעשות סביבה שיש לה כאילו 2? כן, אבל אני לא אוהב את זה שיש לי למעלה אחד לא, למה אחד זה? לא, כאילו זה לא באמת משנה, זה נראה יפה בקיפול, ככה אני עושה בדרך כלל, יש כאילו את החץ הזה, ואז כאילו אני יכול לעשות את זה. זה הדבר שאני ככה. לא, אתה לא יכול לעשות ככה. אם אני עושה סביבה שיש לי תחת השתיים, אז החץ העליון לא מתארך. זה לא כזה נכון. כן, יש לך... לא מדבר בקיצור, אלתר יש אלתר, גאוסיאן אלתר רייטר, וגם אובררייטר. מה? כן, לא, אבל זה דבר כזה... לא, אבל אוקיי, נניח אתה עושה אובררייטר, אז... כן, אבל אני אוהב שהחץ של ה... כן, לא, אבל אז החץ של השואף, העליון, הוא כאילו למעלה, ואני אוהב שהוא באמצע. מה זה באמצע? כאילו, אני אוהב שאני כותב שמשהו שואף למשהו, כאילו שהוא יהיה... אז כאילו... הנה, אתה רואה עכשיו זה חץ כאילו למעלה. כן, אוקיי, לא, סבבה, זה לא טוב, אז תעשה קצת... תעשה פה סיור, ופה נסתור מה שאתה רוצה. אוקיי, אבל אז אני עדיין, אני נניח עושה עכשיו 0, רואה זה עוד יותר גרוע, כאילו החץ מתחת כאילו להחליף. קטן בזה? כן, כאילו יכולים להחליף ביניהם. כן, לא, אבל זה עדיין לא, עדיין זה יוצא לי משהו מעל, אני רוצה שזה יוצא מתחת לשורה. איך עושים משחק לאחר? נעלה לו משהו? לא. בדרך כלל
יש
כזה, אבל זה לא... יש עד 0, אבל עד 0, כאילו, אם אני עושה חץ פה, אז הוא לא... אז החץ לא מתערב.
geology B, cognition B, and deep learning in computer science.
אולי אחד סתם, התיאוריה זה...
It's similar basically. I know that the other four courses are like full-time job kind of, so I just take the seminar, which is like this. Oof! חברה, תגידי שלום. חברה, תגידי שלום. כן. מה אתה משמעת קשור פה? לא, זה האמת.
זה האמת?
לא, זה האמת, אבל טיפה יותר נתחיל, זה איך נראית. כמו לעברת על הנוט, אולי תקנו לך פה. שאלה אם הקורס חמור כבר האמת, מודע המחשב.
יש תקופה משעמת, אבל אם זה לא פה מעניין אותך, יש כאילו כל גם. האמת הוא הרבה יותר שינני, יותר הרבה יותר אלגוריתמי, הרבה יותר תיאוריה של שינני, וזה קורס שמכסה כמה תחומים. סטטיסטיקה, אינפורמציה, חוות וישנניות. אנחנו גם נוגעים בשאלות של למידה, אנחנו גם נראית פאק, אבל בצורה הרבה פחות מעמיקה ממשהו למידה.
מה, פחות מעמיקה?
ספציפית על מודל פאק, בצורה הרבה פחות מעמיקה.
טוב, מודל פאק זה מעניין.
לא, אתמול ראיתי ERM, פאק, DC Dimensions, כאילו חלק מה שאתם אומרים פה.
נכון, אבל בצורה פחות מעמיקה מה שעוברים בהם.
אוקיי.
היה לנו קורס יותר גם, כאילו, מישהו רוצה לעשות דברים שלנו.
איזה ספר ללמידה עצמה, כאילו למידה אנושית, או זה נטו למידה של...
מה את מתכוון?
אני לא מכיר את הקורס, אני לא יודע, מישהו שתמליץ לי לבוא לפה. יש פה נטו משילון, או שיש איזשהו הקשר של משהו לוגי?
אז אנחנו לא... זה קורס תיאורטי, אבל אנחנו בחלק מאוד הרבה יותר אוריינטציה של מדעי המוח.
אז איך אוריינטציה?
אז קודם כל, תראה, זה לא קורס עם אוריינטציה לאפליקציות. היה זה קורס שהתרגילים שלנו הם תרגילים שהם הרבה יותר מעשיים, הרבה יותר אלגוריתמיים, חלקם אפילו אופטימיזציה. פה זה קורס פחות אלגוריתמי. היה גם מאוד עקרונות של הבחירה האופטימלית, של אופטימלית, שהניסיונית, כל מיני דברים כאלה שהם בלב של תורת הלמידה, אבל...
אז את זה אני יודע.
מחר בכלל הביטים שהוא מתחתל, ובכל מתחתל את הביטים הנוריתים ותיאוריות שמשאר. למרות שאנחנו כן מתייחסים, כן לדבר הפעם כאילו כל מיני, אבל זה אולי יש גם ששונים בעוד שי באמת.
קודם כל, לא רלוונטי, בוא נתחיל מזה. הגזעים,
למה הוא רק תסבירי את מה שאמרתי עכשיו? כדאי שכאילו, תחשבי על מה קורה אם זה לא יש מספר חיובי, ואיך יכול להיות כאילו יצא שהרווח תמיד כאילו גדולים, אז יש שם Okay, let's start. אנחנו מתחילים. Okay. So, before the break, we started to discuss the empirical mean. Okay? I will not denote this with n, just x bar. It's the standard notation of the empirical mean. Okay, and we saw that, I erased that, but we saw that the expected value of the empirical mean is the true mean, is mu, okay, and the variance, I erased that, but I'm sure you all remember, was sigma squared divided by n, okay, and when n goes to infinity, the variance goes to 0. So if we get infinite number of samples, the distribution, what can you tell me about the distribution of the empirical mean of this variable? It gets narrower and narrower, okay, and it's concentrated around mu, right? The true expectation, okay? So let's formalize this intuition, okay, by the theorem that is called the weak law of large numbers. Okay, or WLLN for short. Okay, so what I said now is this it's of course we know that the variance goes to 0 and that the expected value is mu. So we know that this random variable would be distributed around its mean, but what the weak law of large numbers tells us that the probability that x bar minus mu is smaller than epsilon, namely that the probability that x bar is close to epsilon, okay, goes to 1 as n goes to infinity. So this already something this already tells us something about the distribution of the empirical mean, right? It tells us that the empirical mean converges to the true mean in probability. Okay? So the probability that we drew a sample and we took the average and we got something that is far than the true mean, more than the error is more than epsilon, this probability goes to 0. Okay? But still this doesn't tell us anything about the whole distribution, just some property of the distribution, and the central limit theorem, which I'm sure you all have heard of, or CLT, tells us that the probability that x bar minus mu divided by sigma is at most z, some value, okay, converges as n goes to infinity to what? Okay, so we know, I'm sure you might have saw this theorem in a different maybe phrasing, that the empirical mean, the distribution of the empirical mean converges to the normal distribution with the same mean and variance, right? So here we just standardized the empirical mean. Okay? So this guy here would be, okay? So this is like, if this was normal, if x bar was exactly the standard normal distribution. So okay, but if x bar was normally distributed, then this would be just the standardization of this, right? And we get z, the standard normal variable. But it's not necessarily normal for finite n, but as n goes to infinity, this is a function. Okay, so the function converges to the CDF of standard normal distribution. Okay, so this is convergence in distribution, while this is convergence in probability. Okay, this means that the value of the empirical mean converges in probability to the true mean, and this means that the whole distribution of the empirical mean converges as n goes to infinity to the distribution of to the normal distribution. Okay, any questions? Okay. So that's that for our probability recap. If you're not sure about something, feel free to raise questions in the discussion forum. I'll upload my notes later on so you can go over them at home if you want. And also feel free to write me if you want to come to my office hours. Okay. Our next topic is related to the things that you have seen in class already. Okay. And we'll focus in this hour on the setting of two world states. Okay? Okay, so I think you saw already in class the problem, or you had an exercise about it. Okay, so suppose we have our domain contains two world states, omega 0 and omega 1. And our set of action also consists of two actions, alpha 0 and alpha 1. Okay, and we can think about this problem as deciding between or predicting what is the true state of the world. Okay, so we have a cost function, right? Lambda of alpha I given omega j. We denote this for simplicity as lambda ij. Okay, and it makes sense to assume that lambda ij, if j is different than I, is greater than lambda ii. Meaning, we pay more if we are wrong. Okay? So we can think about this Bayesian decision problem as a problem that, just deciding between two states or predicting what is the true state of the world, given our observations. Okay? And as you've seen already both in class and in the exercise, what is the optimal decision rule? How do we get, now we observe some x, we received an observation. Okay, so how do we decide which action to take or which state of the world to predict?
So we have the probability of world states and predictions, and we multiply each by the risk, by the cost of each of these decisions, and just compare it to.
Okay, but you got a specific form in the exercise, right? You had in the exercise, you're right, in general, but you developed this a little bit more, and you got that you compare px given omega 0, given that the true state of the world is omega 0, divided by px given omega 1, and this you compared to some threshold, okay, which is p omega 1, the prior over this state of the world, divided by p omega 0 times lambda 0, 1 minus lambda 1, 1 divided by lambda 1, 0 minus lambda 0, 0. Okay? And the nice thing here is that this guy here does not depend on the observation. Okay? So we can just call this theta, some constant. Okay? And if you're non-Bayesian, if you don't want to assume any prior on the state of the world, you don't have to, you can just call this number theta and don't give it don't interpret this as a ratio of priors. Okay? And you're still optimal. Okay? So we take, how do we call this term? This is the likelihood ratio. Okay, so let's denote this by L of x, just the likelihood ratio. Okay, so you simply take, you see observation, you evaluate the likelihood ratio. We assume that we know these two distributions that we are given them. Okay, that's part of the definition of the problem. Okay, so we see an observation, we evaluate Lx, the likelihood ratio, and compare that to a threshold. Okay, and if Lx is greater or equal than theta, then what do we decide?
But if you're not non-Bayesian, how will you come up with data?
Okay, that's okay. There are a few ways. One, for instance, we'll see that in a minute. Suppose we'll define two types of errors, which you already seen in class. Suppose you want to achieve a certain level of error, then you can find theta from that. That's what frequentists usually do. Okay, but this is a bit jumping ahead. Yeah.
What's the definition of lambda I, j not equal to 1?
I. They're different. So if you predict the wrong state of the world, then you pay more than if your prediction is correct. All right? This is just an assumption. It's not always necessary, but it makes sense in this case. Okay. So if Lx is greater or equal than theta, what do we decide? What do we decide? Yeah, and so we decide that the truth is to predict omega 0 or to take action alpha 0. It doesn't matter. And if it's smaller than theta, then we predict that the true state of the world is omega 1. Okay? And you define in class two types of errors. Okay? So what is type 1?
Positive.
Right. So let's denote it by alpha theta. So what do you mean exactly by false positive?
You guess a 1 when it's actually W0.
Right. So it's the you know what? I forgot. Before we talked about the errors, right? This defines as two regions of. Okay. This divides the space of observations into two regions. I need that to formalize what you just said, right? So we have D0, which is all the observations, all x, such that Lx, such that we decide on the 0, which means that Lx is greater or equal than theta. Right? So if we see x in D0, then we decide omega 0. Right? And if we see x in D1, where D1 is all the x's such that Lx is smaller than theta, then we decide omega 1. And now we can formalize exactly what you said. So type 1 error is that we decide that the true state we predicted omega 1, given that the true state of the world is omega 0. So we denote this by alpha theta because it's a function of the threshold, because theta, okay, because these two regions depend on theta. Okay, so alpha theta is the probability that we decide omega 1, namely that x belongs to D1, given that the true state of the world is omega 0. Okay? And this is indeed false positive. And type 2 error. What is that? First of all, we denote it by beta, right, of theta. And what is that? I don't hear. Okay, so it's the probability that we decide that the true state of the world is omega 0, given that it's actually omega 1. So it's the probability that x belongs to what? D0, right? Given that the true state of the world is omega 1. Very good. Let's see where I am. Okay. I assume you saw in class a simple example with between two Gaussian distributions? No?
I don't think we calculated it.
You didn't calculate it for me.
I think you mentioned it. But
You didn't see two Gaussians, like with the same variances and different means? No? Okay. So let's jump to that exercise because that's a simpler one. And then we'll do another exercise that was actually given in an exam a few years ago. So let's start with the most simple exercise. Okay. So suppose we have, so this is just an example. Suppose, again, we have throughout this class, I will assume two states, okay? And so x given omega I is normally distributed with 0 mean and variance 1. Let's say this omega 0. And x given omega 1 is normally distributed with mean 1 and variance 1. Okay, so in this picture, you can think about, suppose this is 0 and this is 1. Okay? And they both have the same variance, so they have the same width. Okay? So just before we evaluate this precisely, just intuitively. Okay? This is the intersection, right? It's exactly between the two means, right? So it's half. Okay, and intuitively, we will decide omega 0 when it's more probable, right? So this is x given omega 0, and this is the PDF, right, of x given omega 1, right? So we decide omega 0 when the density of x given omega 0 is higher, when it's more probable. Okay? So we decide omega 0 here in this region. Right? So this is D0. And we decide omega 1 in this region, so this region is D1. Okay, this is just an intuition. I'll do the calculation in a minute. It's very simple. Okay, I think the intuition here is more important. Okay, so what is alpha in this picture? Again, it's the probability that we decide omega 1 given that the true distribution is given by omega 0. So it's right, and we integrate only this, so it's this part. Okay, until it goes to infinity, of course. Okay, so this is alpha, and beta is just symmetric, right? So this is beta. The green would be beta. Okay, this is just the intuition. Didn't you see this in class? No? Okay. So good thing I asked. So let's do this exercise because it's simple and you'll see that it's not that hard to do the calculation here. Okay, so we need to write down Lx in this case, right? So Lx here is f. Now, since we're talking about continuous random variables, we replace the probability by the density function. Okay, you can show that it holds as well. So f of x given omega 0 divided by f of x given omega 1, and want to compare this to the threshold theta. Okay? Let's write these two explicitly. So f of x given omega 1 is the standard normal distribution, which is 1 over square root of 2 pi sigma. No need to write sigma squared because sigma is 1, right? Exponent of minus half x to the square, because the expected value is 0, divided by 1 over square root of 2 pi times 4, which is times 1 again, sorry. 4 is the next exercise. Okay, because the variance here is the same. Times the exponent of minus half x minus the minus 2 here, which is 1. X minus 1 to the square. Okay? So this and this cancels out. Okay? And we can write this as the exponent of minus half x square plus x minus 1 square greater or equal than theta. Okay? Okay, and what would we like to do now? Log. Okay, this is usually we would like to take the log, so you can take the log on both sides, and we get that minus half x squared minus x squared minus 2x plus 1 is greater or equal than log of theta. Okay, so we can let's for simplicity, just so it's easier and it corresponds to this drawing. Let's assume that theta is 1. But you can also do this for theta, and you'll get an expression that depends on theta. That's not a problem. What? Here? Right. Because, right. This is okay, right? Okay, so in general you can develop this for general theta. We can do that, that's not a problem. But in this drawing, I implicitly assume that theta is 1. Okay, and let me give you the intuition why. Okay, we'll see that in a minute. But if theta equals 1, okay, it means, or we can get theta equals 1 if we take p omega 0 to be equal p, the prior of omega 1, which would be half. And we'll take lambda ij to be delta ij, namely 1 if I 0. Let's write it. Lambda ij to be 0 if I equals j, and 1 if I is not j. And if you substitute this in the bound that we wrote at the beginning, then you get that theta equals 1. Okay? And actually, if you play with the priors, then the intersection here would not necessarily be at half. Okay? You can think about it at home. I just want you to derive the example that corresponds to the drawing. Okay? So this is why I'm assuming here theta equals 1. So if this equals 1, then the log is just cancelled out. Okay? And we get that the bound is x is at least half. Okay? Just do this at home. You can also derive at home the bound for general theta. That's very easy. Okay? Just
Algebra.
Yeah, basic algebra. Simple. Okay? So that's all. That's what we had to do. We had to write the log likelihood ratio, substitute the density function, cancel out terms, take the log, and find a threshold over x. So just note what happened here. Okay, we started with a threshold over the likelihood ratio over Lx. So theta was, do you have a question? Okay. So theta was a threshold over the likelihood ratio, and we transformed this into a threshold over x. Okay? So don't be confused. When we say a threshold test, we mean a threshold over the likelihood. Okay? But in practice, in order to find the decision rule, it's easier to transform this into a threshold over x. Okay? We sometimes call this also a decision boundary. Okay? So here we got a very simple decision rule. Okay? In some cases, the boundaries can be more. It doesn't have to be just. It can be a quadratic equation. Okay, or even more generally, just to illustrate the point that it doesn't have to be threshold over x. It could be not only a quadratic decision rule, namely we compare x to the square to something, but it can also be something crazy. For instance, and this is just an illustration, okay? Suppose, I don't know, this is blue is x given omega 0, and green is x, I don't know, given omega 1. Okay? So just intuitively, what would be the D0 and D1? Okay, so now there are union of segments, right? So we have here, yeah, suppose the products are the same. Okay, that's an important assumption. Otherwise, it just shifts the fraction between the two distributions. Okay, try to think about it at home. What happens if we change the products? Okay, so we have here many segments. Okay, so in this segment, for instance, we decide omega 0, but if the true state is omega 1, then we need to sum it for alpha, right? So these regions, okay, in black, are all accounted for alpha. Okay, and the other regions, you need to sum them to find beta. Okay, so in general, the decision rule can be crazy. Okay, it doesn't have to be so nice, but it's nice when it happens. Okay, in the next example that we'll see now, we'll also get a nice decision rule. Okay, so this is a question from an exam from 2004. By the way, questions? You're quiet because it's all clear? Okay. Okay. Let's go back here. Okay, so this is another question. Suppose now that x given omega I, there are two exponential distributions with two parameters lambda I. Again, we have two states. So we have lambda 0 and lambda 1. Okay? And let's assume for simplicity that lambda 1 is greater than lambda 0. Okay? So we want to A, find the decision boundary. And 2B, we would like to find beta. Okay? So let's solve this question. This was from 2004A. So solution. Okay, so how do we find the decision boundary? How do we start? Right. So we want to write, so to solve A, we want to start by writing the log likelihood, Lx. Okay? Which is, I remind you, f of x given omega 0 divided by f of x given omega 1. Okay? So now I need to substitute here the PDF of the exponential distribution, right? So help me out. Lambda 0, exponent of minus lambda 0 x divided by lambda 1, the exponent of minus lambda 1 x. Okay, we need to compare this to some threshold theta.
What happens to the lambda factorial that are supposed to be on the bottom?
That's the exponential distribution, not, what do you mean lambda factorial? In the Poisson, it's not Poisson, and even in Poisson, it's not lambda factorial, it's k factorial. This is the exponential distribution. Okay. Okay, so we can now write this as exponent of lambda 1 minus lambda 0 x. That should be greater or equal than lambda 1 theta divided by lambda 0. Okay, and now what we would want to do, take log, right? So from here we get that x, I'm taking the log and dividing, okay, and we can divide here because we assume that this is this. Okay, so we can just divide by lambda 1 minus lambda 0, and then we simply get that x needs to be greater or equal than log of lambda 1 theta minus divided over lambda 0 divided by lambda 1 minus lambda 0. Okay, and this is our decision boundary, and let's draw this. Okay, before we evaluate beta, let's do a drawing. Okay, so this is x, this is 0 because the exponential distribution is positive, is over the positive real numbers. Okay, and this is we'll draw here f of x over the two states. So suppose this is lambda 1. So the exponential distribution looks something like this. Okay, decays to 0, of course. And suppose that this is lambda 0. So the exponential distribution in this case would look something like this. Why does the lambda not depend on the action? What do you mean? Oh, this is not the same lambda. This is not the cost. Okay, it's confusing, I know. But this is the notation. We denote the parameter of the exponential distribution by lambda. Okay, it's not the cost function. Thank you for clarifying that. Very good. Okay, so let's call this guy here, let's call this t of theta. Okay? So this is here t of theta. Right? Now, here in this region, this is d 0, 1, 0, right? Because we derived this condition for deciding omega 0. Okay, so if x is greater than t theta, then we decide d0, and this here is d1. Okay? So on this drawing, what is alpha? What is alpha? So alpha is the probability that we decide d1 given that the true distribution is d0, right? So it's this region. This corresponds, integrating this corresponds to alpha. And what is beta? Is integrating, let me draw this maybe in blue. To find beta, we need to integrate over this region. right? So that will be beta. Questions? Yes.
How do you see that the intersection of the two PDFs is exactly the boundary?
Right.
Intuitively.
So you're right that in general it doesn't have to be exactly on this intersection. It will be exactly if the priors are and the costs are 0, 1. Yeah. So then it will be exactly. You're right. So this is just an illustration, an intuitive illustration, but it can change. If you change the priors, if you change the cost, then you shift the threshold. That's an excellent point. Okay.
You sure alpha and beta are switched? Maybe.
Let's see. The blue is the probability of x given omega 0, and in this region we decide omega 1. So integrating this is integrating over all the observations in which we decide omega 1, but we integrate just over the blue PDF. Okay? So it's alpha. Okay? So let's find beta. I think we're ready for that now. Okay, so how do we find beta? We need to integrate, right? We said that beta is this. We need to integrate from t theta to infinity, right? So it will be the integral from t theta to infinity of what? Of the PDF of x given omega 1. It's beta. Confusing, I know. Okay? It's very confusing. It's okay. So let's okay, so just notice that this region here, how can you, in terms of the CDF of the exponential distribution, how can you, okay, so if, let's draw a small drawing here. Okay, so suppose this is the exponential distribution. Okay, this is some threshold, t. Okay, so this region, okay, is 1 minus this region, right? Because this integral plus this integral must sum to 1, and this region is the CDF, right, of the exponential distribution. It's the probability that x is at most t. This is t. So it's 1 of the CDF, let's write it f of t. Okay? So this is just 1 minus f of the exponential distribution, of course, of t theta, okay, which is 1 minus the exponent of minus lambda, let's write it 1, because it's the CDF under omega 1, right? So it's lambda 1 t theta, okay, which gives us the exponent of e minus lambda 1 t theta. Okay? And if you just substitute t theta, you'll get an exact term. Okay? Any questions?
Over here we don't assume anything about theta, right? We don't need to calculate it in any, like, before you said like theta equals 1.
Right. So okay. So you can go in two ways. You can say I'm Bayesian, so I have a cost function and I have priors, and this is how I choose theta. You can say no, I'm not Bayesian. I don't want to assume any priors. Okay. You're right. I have a degree of freedom of choosing theta, but I do want to find a test that reaches a certain level of confidence, right, or significance. So I want to choose alpha, such that.
So alpha will determine.
Exactly. Okay. Exactly. I don't know if we have time to. I'll put in my notes a simple example of how you can find theta from alpha. Okay, so if you set it to an alpha, how you can find theta. You'll find it in my notes because we don't have enough time now. If you substitute this, what that?
Did we find alpha anywhere here?
Did we?
Find alpha?
No. Right, we only found beta. You want to find alpha? Let's do it together. What will be alpha theta in this case? It will be the integral between 0 to t theta, very well, of f of x given omega 0, very well, and just substitute here. This is actually simple, right? It's the CDF of the exponential distribution under omega 0, which is 1 minus the exponent of minus lambda 0 t theta. Okay? And just substitute this specific value and you'll get a nice result. Oh, I don't know, some result. It is only a function of theta and the lambda. Okay, any questions? Okay, so probably tomorrow you need to submit exercise 1, and after that we'll publish a new exercise for 2 weeks. You will have a simple programming task. I hope it won't be too hard, but this is why we're giving you more time, so don't worry. Questions? Okay. לא. שבועיים, fine.